Now that we've looked at the structure, functionality, and key methods in Java StampedLock, let's take a look at how you could apply it in practice. And this is going to show off a bunch of interesting use cases that are actually covered in the Java documentation. So if you go take a look at the Java documentation, you'll see these examples, but of course, I've gone through a bit more detail to walk through them kind of step by step and explain them. So the examples are all based on something called the point class. And the point class would just be a simple class you could use for some kind of GUI environment or some kind of geometry environment where you've got two values, X and Y, maintains two-dimensional points. So X and Y, which are doubles in this case, are the state that needs to be protected. And we're going to protect it by a stamped lock. So the stamped lock will be doing the protection. So let's first take a look at how you can use stamped lock in so-called writing mode. So let's say that we have a method called move, and the idea of move is to give it new X and new Y, and we want to update X and Y by the delta that are passed in as parameters. So this again is a pessimistic method. Therefore, we first acquire a write lock because we need exclusive access to do this. With that write lock acquired, which could block, but let's say once we've got it, we then modify the state atomically, and then we go ahead and release the write lock. We call unlike write because we know we have a write lock, so that's the fastest way to do things. All right, that was pretty simple, but that's really no different from just using a good old reentrant lock or using a good old Java synchronized statement or synchronized method. So let's take a look at some more interesting examples. This example is going to demonstrate an optimistic read with a stamped lock. And the particular method we're going to look at here is one called distance from origin. So this one is going to be optimistic, so the glass is half full. And the first thing we do is we attempt to get an observation stamp. That's what you get back when you call try optimistic read. So we make that call. And then after we make that call, we're going to copy the value of X and copy the value of Y, which are the fields in the point class, into local variables that are local to the distance from origin method. So now we have cur X and cur Y. And remember, try optimistic read was nice and it made sure that X and Y are the latest values, but now we're going to go ahead and stash them away in these local variables. Now, what we're going to do next is we're going to call validate. If no write lock has been acquired between the time we call try optimistic read and we call validate, and notice that's a very small window, right? That's probably talking about nanoseconds. If nothing has changed and these things have not been modified or the write lock has not been held, then validate will return true. But if for some reason they were changed, then what we're going to do is we're going to go ahead and block acquiring a read lock. So if there was a write lock, then we're going to block and acquire a read lock, and that may block as long as the write lock is held by another thread, which probably won't be very long, but it would require some blocking potentially. With the read lock now held, we're going to go ahead and make copies of X and Y using pessimistic reads, and these are ones that are protected by that read lock. And then finally, we're going to go ahead and unlock the read lock if we had to acquire it at all. Note that if validate returns true, we never acquired a read lock at all, so there's no need to unlock anything. So if validate succeeded, there's no lock operation, which is why it's much more efficient if there's no locking. Then we go ahead and we do a square root, which does the computations with the values that we copy. So they'll either be optimistically still fine because we validated them, or we'll end up in a situation where we acquired the read lock. So in either case, we know that we've got valid values, although they may not be the freshest values, but we know that they're not corrupted. And then the final mode we're going to look at is the so-called conditional write mode. And this is going to be an interesting method called move if at origin. So we're going to give it new X and Y coordinates, but we're only going to move if we're at a condition where the current value of X and Y are 0. So the first thing we're going to do is we're going to acquire a read lock because we want to make sure that we can read these values of X and Y with shared access so that nothing will be corrupting them while we're reading or changing them while we're reading. And then we go into a loop and we check to see if X and Y are at the origin. In other words, they both have the value of 0. This loop will only execute at most twice, and you'll see why it does that in a moment. So if X and Y are 0, then what we're going to do is we're going to try to convert to a write lock. which is going to attempt to atomically upgrade to a write lock without blocking. And what's important to note here is that try to convert to write lock will atomically release the read lock that it holds, because it got the read lock up here. And it will acquire the write lock if and only if there are no other readers at that point. Now, if we end up getting back a non-zero, that means that it succeeded. So if we were able to upgrade without blocking, we then go ahead and assign this write stamp to the stamp, and you'll see why we do that in a second. And then we go ahead and modify X and Y to be new X and new Y. And then we break out of the loop. Otherwise, we were not able to atomically convert the read lock to a write lock. So what we do here is we unlock the read lock, and then we block acquiring the write lock. So that will then block until we've got the write lock. So the X and Y values may change between the unlock, read, and the write lock, and therefore we're going to have to loop back around again and retest the condition. And that's why we do this in a loop. And that's why it only loops at most twice. And that's because the second time around, we've got a write lock. So at that point, now that we've got a write lock, when we do try to convert to write lock with a write lock stamp, that will be guaranteed to succeed. And in that case, then we've done our thing. And at this point, we will release the appropriate lock, which will either be a read lock or a write lock, depending on whether or not we were able to do that conditional write upgrade that we saw before. So this is a good example of when to use the unlock method, because we don't really know, unless we do some extra state manipulation in our code, if we have a write lock or a read lock at that point. But the nice thing here is that unlock keeps track of all that for us. So that's the end of the example application of Java StampedLock. I think you'll agree with me that this is very cool, very powerful, but also complicated. And so to really master these different modes, you have to get practice with it. And of course, that's what you're going to get with assignment 4B, is you're going to end up implementing a Palantiri manager that's going to use these different locking modes to implement the methods that you have there, like the one that does acquire the Palantir, the one that does the release of the Palantir, and so on and so forth. So it'll give you a chance to really experiment with this and get a good feeling for how it works in practice.